Thank you for the introduction, and as the talk suggests, I want to show how to work on quantum computers. And more concrete, first I want to show what you need, what ingredients, how it's experimentally realized on one example. And then finally, how you can run programs and algorithms on a quantum computer. And especially the last step is very exciting to me, because as a theorist, most of the time I'm sitting in an office, and so I have at least sometimes the illusion that I can work on an experiment and see what comes out. Before I want to dive into these topics, I want to show possible applications for quantum computers. I mean, the most flashy one most of you know is, or have at least heard of, is concerning prime factorization using Shor's algorithm. The idea is that this is an algorithm which factorizes prime numbers exponentially faster than any known classical algorithms. And that's also the reason why, for example, the military is interested in quantum computers, and the funding is quite well in this field. But because it could, in principle, break public key encryptions. But to be honest, this application is quite far in the future. I guess it will take at least 20 more years or even longer until you can make real use cases. What is more exciting from a physical perspective, and this is also what Dominik, for example, mentioned in this talk, is this simulation of strongly interacting quantum systems. So in these cases, you have often many competitive terms, like the kinetic terms and interactions. And so you have not the dominant term where you can apply perturbation theory on. And in these cases, it's hard to apply classical algorithms. And this is where quantum computers come into play. One example are the strongly correlated systems Dominik mentioned before. They are interesting because one of the most open problems in physics, like high temperature superconductivity, are buried in these models. Another model, also mentioned a little bit before, is concerning quantum chemistry, which are also strongly interacting orbitals and are hard to simulate classically. But also, when you consider high energy physics, I mean, you have, in order to understand this, you have to build large colliders, or you can do, to some very limited extent, some classical simulations, which goes then as lattice QCD. But these classical simulations are very hard to realize. You can only consider limited systems and so, and you have to put much effort into this. And it turns out that there are also algorithms to simulate, for example, the standard models, and there's active work on it to realize it in quantum computers, and it's probably at the long term a cheaper way than building the next largest collider. With this in hand, I want to show what you need, and this was nicely summarized in DiVincenzo's criteria roughly 25 years ago. The first thing is that you need qubits which are scalable. So which is basically the building block of a quantum computer. That's nothing else than you need classical bits for a classical computer. The second thing is that you need long enough coherence times. This you need that you actually can use the laws of quantum mechanics to run algorithms which are hard to simulate in classical computers. And it turns out that this is actually the most challenging issue for current realizations. And you probably need quantum error correction in the long terms to tackle this challenge. This was also mentioned in a talk last year by Benedict, so I will only briefly touch this at the end of the talk. then you need a universal set of quantum gates. And for a quantum computer, basically the idea is that the algorithms consist of unitary operations, and then you need some ingredients to realize them. And it turns out that you basically need single qubit gates, which are the Hadamard and for example, a phase gate, a T gate here in the bottom, which I will illustrate later. And then you need two qubit gates, which can entangle qubits, which is in this case a controlled knot operations. And with this universal set, you can build arbitrary unitary operations. And finally, to get also something out of your quantum computer, you have measurements to get some results and compare what they are giving. So in the last 20 years, there were lots of proposals and approaches to satisfy this criteria. I just mentioned a few, the few probably most promising right now. One are superconducting qubits, which is a strategy pursued by companies like Google, IBM, also here in Oxford. And the idea is that you basically use electrical circuit elements involving Josephson junctions and encode the qubits in these circuit elements. I will explain this later. Then you can, another possibility is using trapped ions, where you store the qubits into energy levels of these ions and then apply pulses to manipulate these levels. There was recently some announcement that you can use topological quantum computing by Microsoft. I do not want to state now whether these claims are correct or not, but if this were the case, this would be also quite a promising realization, which is easy to scale up. Another possibility is using ultra-coiled atoms with neutral atoms in contrast to the trapped ion case which we had before. But it emerged, especially in the last 5 years, as another competitive player in the field. There are lots of other approaches. For example, photonic quantum computers. There are attempts to use silicon quantum computing and so on. But I cannot explain all of them because of a lack of time and because I heard that there's lunch served later and I'm also hungry. So I will focus right now on superconducting circuits, qubits. So here in this picture, you essentially can see for transmon qubits, or more specifically, this cross-shaped form. And when you zoom in a little bit, you see at the order of meter, hundreds of micrometers. You see this cross shape. You zoom in even more, and then you see what you actually see, which has the size of a few 100 nanometers. Is basically a Josephson junctions, and the cross shape. This is basically a large capacitance. And the idea is that this Josephson junctions is a nonlinear conductivity of your circuit, which will become later. And when you do some elementary physics in this for the circuits, you can quantize the Hamiltonian corresponding to the system. And this has basically this form. So the first part corresponds to the capacitance energy. And is the number of Cooper pairs on the islands, and the second term is basically a term coming from the Josephson current of these junctions. But what is very important is when you look at this point that it's not quadratic, but it's a cosine. which is basically almost an anharmonic oscillator. And which is also important is that the number of Cooper pairs in the Josephson phase, they are conjugated variables, so you get almost something as the harmonic oscillator. Now when you look at this model and compare it with a harmonic oscillator, there you have a quadratic potential, and as you know from your first courses in quantum mechanics, for a quadratic potential you get equidistant level spacing. Now the cosine potential looks almost like this harmonic potential, but not quite. So what you see is that you have a slight distortion of these energy levels. And the qubit itself corresponds to the lowest two eigenstates of your transmon qubit. So with this in mind, we can try to understand how you apply quantum operations on these levels. For this, I consider single qubit operations. Two qubit operations are similar. Basically, what you have here is a cavity, and you couple your transmon qubit to a resonator. What happens is basically that you get a hybridization between the photon and the qubit states, which means they are no longer independent of each other, but you get a slight dressing, similar to this quasi-particle picture Dumitru showed before. To lower the approximation, you can still separate them, but what happens is that basically by applying a photon pulse, you can change the state of the transmon qubit. So you're basically applying here microwave pulse and then introduce transitions in the qubits here between the first and the second state. Here, this is a point where this anharmonicity becomes very important in the sense that transitions between the lowest two eigenstates are allowed, but transitions to higher states, they are slightly off resonance, which means that they are strongly suppressed. So you avoid that you excite higher levels and leak information of your qubits. When you want to apply two qubit operations, this can unfortunately is not visible here in this picture, but basically you have cavities between different qubits, and then you can also you can drive one qubit and with your microwave pulse, and the effect depends then on the state of the other qubit. Finally, we have to consider measurements. For this, you have here this other resonator, also coupled via cavity to this transmon qubits, and there the concept is also quite similar. So, because of this coupling, the states of the transmon qubits are no longer completely separable of the microwave pulse. And on the other hand is also that the eigenmodes of this resonator depend on the qubit states. What it explicitly means is when you look at the transmission frequency of your resonator, which you can just measure by applying a microwave pulse, then you see that it has a given resonance state if the qubit is in state 0. But it's getting shifted when the qubit is in state 1. And basically, by reading out the transmission frequency, you can measure the qubit and infer in what state it is. So with this in mind, we can we have basically everything to run algorithms and perform quantum operations on our quantum computer. The basic operations which you have in this case are often illustrated in circuit diagrams. I want to briefly sketch how they look like. I mean, easiest case is when you consider qubits. They are basically denoted by a black line, as you can see here above. When you consider now quantum operations, they are illustrated by boxes, and there you get again the protagonist I have showed you already before at the beginning. All of them are unitary gates, as you would expect from the laws of quantum mechanics, and this is basically the only restrictions you have for these operations. The most illustrative one is, I think, is the NOT gate or the X gate. This is very similar to what you expect on classical circuits. Basically, when you write it as a matrix element, what this operation is doing is when your qubit is in state 0, it flips it to state 1, and otherwise it flips and vice versa. Then you have Hadamard gates. The idea of this Hadamard gate is it looks slightly more complicated, but basically what it is doing when you start in the ground state of your qubit, after applying a Hadamard gate, you will be in a superposition between state 0 and state 1. And what I mentioned before, you need some additional gates which can induce additional phases between the states of the qubits, and this is done by phase gates, or specifically when you have a phase shift of pi4, is done here, then it's called a T-gate. And it turns out when you basically when you only apply Hadamard or T-gates, you can create arbitrary 1-qubit rotations by stacking it together, which has been shown roughly 30 years ago. Now, 1-qubit operations are, they might be interesting, but you cannot do so much useful things with 1 qubit. I do not have to build a quantum computer for that. So you need interactions between qubits. And it turns out that when you have add another gate, which is a C0 gate, which is shown here, which basically this C0 gate shifts, induces a transition of the second qubit only when the first qubit is in an excited state. And it turns out when you add this C0 gate to your circuit, then this is already sufficient to create arbitrary unitary transformations with an arbitrary number of qubits. And finally, as mentioned, you need measurements which are basically indicated by this box. Now, I do not only want to implement them classically, but I'm also interested to run them on real devices. And it turns out that there are a solution. So what you can do is that, as I will illustrate in a second, is that you can program your quantum circuits with a Python library, which is called Qiskit. And the idea is basically you construct your circuit, then you submit it to a compiler, which will translate your circuit to native gate operations of your quantum computer, which is very similar as you are doing for classical coding. And then basically you can analyze the circuit also with Qiskit. When you have small-scale simulations with order 10 qubits, you can simulate it classically, which is good for debugging to see whether you are doing the right thing. But many of these companies, they allow access to real hardware via cloud services. Notably, there is AWS Bracket, which allows access, for example, to Google or Quantinuum quantum computers. But there's also access to IBM Quantum. And what's interesting is that you do not have to be a professional. In fact, everybody can register for this service, and you have also a limited number of time to run operations on these quantum computers yourself. In fact, I think I know in the case of IBM Quantum, it's you have 10 minutes time of computation time per month, but this is sufficient to run small operations, and also everything what I will show later is done within a few minutes. When you look at this quantum computers, this cloud services, they illustrate how the qubits are connected. This is a snapshot of IBM Kiev, which has 126 or 27 qubits, and in principle you can use all of them. And it turns out that this is already hard to simulate on classical devices. Finally, and this I also want to advocate, you can do it on your own, and it turns out that programming quantum computers is not that much different to programming classical computers. To show this, I want to illustrate first a very simple example, which is creating a base state, which is basically that either above qubits are in state 0 and above states are in state 1. So so it's not very complex, but in principle, this creation of such states was very important also to test causality of quantum mechanics, and also resulted in a Nobel Prize just a few years ago. It turns out when you want to run it on a quantum computer, you first import a quantum circuit object. You basically import your library, and then you apply your gates quite straightforward. So in order to create your base state, first you have to apply a Hadamard gate to the qubit 0. So you put it in the first qubit on a superposition of 0 and 1. Then you apply a controlled NOT operation, which basically means that the first qubit is then in state 0 when the 0th qubit is in state 0 and vice versa. And then you perform a few two measurements to read out the qubits. That's basically it, and then you can test how it looks on a quantum computer. So it's 5 lines of code. Now we want to execute this. I mean, you can do it either classically simulated. For this, they provide classical simulators. If you want to directly go to a quantum computer, you do not have to change much. It's basically changing 2 lines of code. And then the next step is what I mentioned before. You have to transpile or compile your circuit. For this, you call a transpiler. Basically, this transpiler has information of the quantum computer you want to run your code, and it translates your circuit to the native gates of your quantum computer. When you do it, in this case, I have prepared this in advance. The circuit looks like this. What you have basically is that this C0, this is translated to such a 2-qubit operation, which is almost a C0, apart from some additional phase shifts. And then the single qubit operation is translated in a lot of rotations and additional phase gates. What is also interesting is when you look at the circuit, there are 2 numbers, 49 and 50. And when you look at the quantum computers I have shown before. It means basically that the circuit is run on these 2 qubits you can see here. And then, I mean, apart from that, you basically submit your job. In our case, we want to run this circuit multiple times to get some statistics and see what comes out, and then you retrieve the result, which encodes some information, what gates you used, of properties of the quantum device, what noise rates it has, and also, of course, the result itself, and then you can show it in a histogram. In this case, I have prepared it, as I mentioned. When you do the classical simulations, you get basically this count. I repeated the simulation 1,024 times. This is basically a matter of seconds for these circuits. And what you can see is that you have basically 520 times you measure the qubit in both qubits in state 0, and otherwise you measure it in state 1. I mean, it's not perfectly 50%, but this is basically to statistical fluctuations. Now you can do the same on a real device. And in this case, you see, make this observation. It looks almost the same. You get almost 50% on state 0, above qubits on state 0, above qubits on state 1. But what you also see is that there are slight deviations, basically that only 1 qubit is in state 1 and 1 qubit or the other one. And this is basically due to noise and hardware errors, which is quite remarkable. What you have seen before was a very small circuit, and we have already 2% error rates, which gives you an impression how good current hardware is. So, I mean, this is basically the reason why we have to deal with errors in the long run. I mean, as mentioned, this was very simplistic example. Now I want to show you something which is more connected to real world, at least from a theorist's perspective. This is basically dealing with quantum dynamics, which is one of the most promising applications. Basically, use a quantum computer to simulate other quantum systems. And the idea is that you use a trotted decomposition. So usually you have a very complex operator or a complex system, your molecule or your strongly interacting systems Dominik has shown before. And what you can do is that you decompose this big block or these Hamiltonians in a bunch of 2-qubit operations. And when you have these 2-qubit operations, it's in straightforward to build this and compile, and then you can run this. I mean, this looks quite simple, but the issue is, from a classical perspective, that the dimension of the Hilbert space scales exponentially with the number of qubits. And when you want to simulate such systems classically, it turns out that you're basically at the limits of state-of-the-art classical computers when you go to roughly 30 qubits or a bit more, which is, I would say, quite far from complex molecules or interacting systems. So that's a reason why this approach is actually used also to benchmark the performance of quantum computers. And when you do a few tweaks and tricks, you can show already that current quantum computers can give competitive results to classical devices. How is this done? Again, using Qiskit. I use a very simple toy model, but it's straightforward to use something more complex. In fact, this case is so simple that you can solve it exactly by hand. So you have basically an interaction between 2 qubits by some XX interaction, and you have some additional magnetic field. And when you want to code the trotter evolution, what you have to do is you basically create a trotter gate. So you create your Hamiltonian with one line, or the 2-qubit Hamiltonian, and then this automatically creates you this 2-qubit evolution gate. And when you want to multiply it multiple times, you have basically add a few lines of code which apply your gate either to the even bonds, which are the first 2 lines, or to the odd bonds, and that's basically it. So I can show again, when you want to consider one of these trotter steps for 6 qubits, it looks like this. I mean, it's a bit more complex than before, but when you look closely at this, then this red box corresponds to one trotter step, which I have implemented, and the rest is done by Anton Speiler. Now you can again compare the time evolution as I have done before. In this case, I show do not sample the exact strings, but measure the magnetization. So the expectation value for Z on each side. When you do it classically on the exact simulation on a classical computer, I start with a staggered initial state, which is indicated by this alternating pattern. And when you evolve in time, you see that the system equilibrates, but you see also this long-term oscillations. Now you can compare it again with a quantum computer. It looks not that bad, in fact, especially when you have in mind that before we have a 2% error rate per gate. So you see, especially at the beginning, you see these oscillations. There is 1 qubit where this oscillation do not decay really, which indicates that probably this qubit does not work properly. But additionally, you see that the long time values it seems to equilibrate, but you are not able to capture the oscillations, at least when we do it as naively as I did right now. But still, in comparison to the base state I have shown before, it seems that especially when you look at observables or so, it performs relatively good in comparison what you would naively expect from 2% errors per step. And this is also basically an indication that when you consider physical systems or so, that they are basically more robust to errors than you would naively expect. Now, I showed you how well or bad the quantum computers are, and as you have seen, you have lots of errors. So I want to briefly sketch at the end of my talk how to deal with them. One thing, and this is basically the path to go in the long term when you want to run more complex algorithms, as for example Shor's algorithm, is that you have to do quantum error correction. The idea is basically you instead of using 1 qubit, you encode redundant information, basically repeat the information of the qubits in multiple qubits, such that you can detect when you have an error and correct for it. And this has been shown by Benedict last time. But this, in order to do this, you basically require quite small error rates and large number of qubits. Basically, the reason is when you increase the number of qubits, you also increase an error rate, and so you basically have to balance this. And I mean, this is an active area of research. This is, for example, a picture of encoding 1 qubit in terms of roughly, I think it's 50 physical qubits, and then detecting the errors. But the point is, I think in order to get this work, you will need at least a few more years. Another promising thing, which is probably more applicable in the short term, is so-called quantum error mitigation. As you have seen before, for observables, it seems that we do not need the perfect quantum computer. And the idea is that you run experiments to learn the noise and then do some interpolation. This idea is basically quite simple, and it is also not more. Basically, what you have, you start with a noise rate 1, which corresponds to the noise you have on an actual quantum computer. And when you know how your errors build up, you can basically artificially enhance your noise rate, as is done by these red dots, red crosses. And then you can interpolate to 0 noise rate. And that looks often a bit fishy, but it seems that it works pretty well for observables. And when you want to be competitive with classical simulations, and this is the method which is done to get good results on quantum computers already today. To sum up, what I wanted to highlight is that basically programming a quantum computer is quite simple, so everybody can do it. I mean, this is a code for a trotter step, which is only a few lines of code, and then you are basically often already at the forefront of research. And the remaining main challenge you have to do is understanding the error, and which is where most efforts are right now. Thank you for your attention, and do it yourself. Okay, so basically the question, as far as I understand, is whether there are possibilities to, or whether it's worth to think about improving quantum gates and how fast you can do it. Yeah, actually, that's a good point, and I mean, I think that's the main difference between different approaches of quantum computers. When you look at the execution times of gates, in the case of superconducting qubits, it's of order hundreds of nanoseconds. When you use trapped ions, it's basically 3 orders of magnitude larger. And I think one of the most important properties, especially when you have trapped ions or so, is finding approaches that you can reduce the execution time of gates. And this is also basically cutting edge of research, not for the superconducting qubits, but for other devices. Okay, the question is basically whether you have different language constructs to different types of quantum computing. So far, I think the issue is a little bit that the quantum computers are still in such native stages that I think there is so far no need to think about more advanced cases. I think it might be the case when you will go to more complex algorithms and how to implement it. There are, for example, proposals that instead of gate operations, you only perform measurements, and this might be sufficient to generate universal quantum computers. So in this sense, it is thought about it. But in principle, it's mostly that we are only at the single qubit and 2 qubit stage, and so it's a bit early in many cases. Yeah, I start with it. So basically, the question is how does quantum error correction work? Yeah, you need physical qubits to get a logical qubits, and then you run in increasing required coherence times. How does it work? That's a good point, and that's also the issue why we do not have quantum error correction right now, to one point. The point is that the way how it works is when you have a sufficient number of qubits, then basically you can correct a small number of errors. So this helps you, but at the same time, as you mentioned, you have increasing sources of error. So you have basically two factors. What turns out is when your error rate of physical qubits is large, then you have no chance, and then trying to do quantum error correction will kill you. However, right now we are at the stage where basically quantum error correction wins. So you basically by adding security, by adding qubits, you gain as much advantage that it basically overtakes the disadvantage from more additional physical qubits. And also concerning the question how many physical qubits you need to protect one logical qubit. So it basically when you are below this threshold, where logical quantum error correction wins, what you can see is the more physical qubits you use, the exponentially better becomes your advantage. And then it's basically trying to be as good as possible with the physical qubits, and then it might be that you need only a few more physical qubits, but it's still work in progress. In fact, I think the state of the art for superconducting qubits is that you can generate one logical qubit. Yeah, so the question is, can you gain advantage when instead of using qubits with two states, whether you can gain advantage with 3 states, qubits, or even more states? This has been explored, and there are also possibilities. I mean, I think for most long time approaches, when you are sufficiently efficient, it will maybe make a difference of a factor. So from a computational complexity point of view, it will not change. But what has been explored is, for example, when you simulate lattice gauge theories, which is important to study high energy physics, or the physics of the standard models, then especially when in trapped ion systems, it's easy, instead of controlling 2 qubits, 2 levels, controlling multiple levels up to 20 levels. And it turns out that in this case you can gain a massive advantage in the length of the circuits and get more efficient computations. It's a good observation. So the question is, but I go just quickly back. Basically, I show results here for multiple time steps. How does it work? When I measure the state, I actually destroy it. And that's a good point. And the answer is that I have not run here one experiment, but 30 experiments for each different system size. So basically, in advance, I state how many trotter steps do I want. For example, for 10 trotter steps, which corresponds to time t equal 10, and then I run this experiment. In this case, I run it 1,000 times to collect enough statistics, and then I get the measurements. Of course, I mean you get a massive overhead. But it's doable. So in principle, for one time step to generate 1,000 measurements, it took me 10 seconds on a quantum computer. So I think the overall plot on the right is a matter of 5 minutes or so. Yes, exactly. So I think that this cube, and this qubit does not work. And actually, when you look at this IBM quantum website, you can have access to the performance of these qubits, and what you will see is that sometimes there are some miscalibrations, and not all of these connections are perfect. And this is what happened here. Yeah. So I think the point is, I mean, it does not work for actual classical encryption. Well, you could break you can break the RSA encryption, but the reason why we use it right now is because it's relatively cheap to implement. But there's current research of post-quantum cryptography, which you cannot break with quantum computers, and would be secure because of the physical laws of quantum mechanics. I mean, nevertheless, I mean, probably for most cases it's too expensive, and it's why quantum computers still might be useful in this field a long time. But when you have very, very sensitive information, you would use a different encryption.
Not your research.
No, I think not mine. But I think it's a reasonable concern, and it is also when you look at the research that it's, for example, often classified in the US. Also, when you travel to China and tell you're a quantum researcher, they are very interested in you. Okay, the question is basically what is more important? Is it understanding errors and try to cure them, or is it basically getting larger and better quantum computers? But which is more important? The point is when you consider this error mitigation techniques I mentioned before, I think they help for some cases as observables, but I think they will ultimately break down at some point, and you can also show that they will not rescue in any cases. So I think in the long-term run, you will always need quantum error correction and better quantum computers. But nevertheless, when you look at the near future or so, what will happen is that you basically have an interplay of these two approaches, that error mitigation will help you to be a little bit better, and then you will get a fast improvement with quantum error correction once it is here. Okay, that's a good question. The question is basically whether I'm, as a programmer, responsible for quantum error correction, or it's done in the compiler or on the hardware level. I mean, that's already shown here a little bit. What happens with time is when the progress in quantum computer evolves, is that basically more and more is getting a black box. I mean, already here, I mean, you see that I basically create a Pauli evolution gate by calling another comment. So 2 or 3 years ago, I had to code it up myself, and it was a bit more complex. What I think also with this quantum error correction is it will basically go down either to the compiler or even lower to the hardware level. To what level, I do not know exactly.
All right, it looks like we have run out of questions, so let's thank Dominik.